As the final lecture of this crystallography of materials, I will systematically derive the 32 point groups. Point groups is basically when there is lattice points, and then what kinds of symmetry elements can be available without moving it, just surrounding these lattice points. And when we derive this, basically there's two different operations. One is right hand goes to the right hand with just a simple rotation operation. And there is the operation which makes right hand to left hand. I explained to you about the inversion center makes right hand to left hand, and any mirror plane can do the same thing. When you do the mirror plane operation, the right hand become to left hand. By combination of all these rotation elements and multi-rotation elements, and the mirror plane and inversion, what kinds of symmetry elements are possible just surrounding this one lattice points, point group. Then we can have 32 point groups, and I will systematically derive these 32 point groups one by one. Before doing that, there are a few principles that we have to remember. One is when two mirror plane, M1, M2 mirror plane, has certain angles of mu. So we have two mirror planes with certain angles of mu separations. Then when these two mirror plane touches, then there is lines of these two mirror plane intersects. That's the projection of this A point. A point basically defines the lines. Then when there is an M1 mirror plane, if we have 1R right-hand objects, then right-hand objects become 2L by the symmetry operation of M1. And this 2L become 3R by the symmetry operation of M2. So this two successive operation of two mirror planes, which has angle of mu, then this is the same as 1R goes to 3R, then this angle should be 2 mu. Okay? So when there are two mirror plane intersects with an angle of mu, then the lines where these two mirror plane meet has 2 mu rotational symmetry elements. Okay? It's so just one principle that we can easily remember. So when there are two mirror planes with alpha over 2 angle separations, then the lines which intersects of this mirror plane has alpha rotational elements. Another fundamental things that we have to remember is the mirror plane and the inversion center operations. When there is a mirror plane and there is certain axis, then 1R operation become 2L, right hand become left hand by the mirror plane operation. And if there is an inversion center at this position where this line intersects with this mirror plane, then 2R becomes 3R. So mirror plane operation and the inversion center, successive operation of these two symmetry elements, meaning that these lines has pi rotational symmetries. Okay? So mirror plane and inversion center is the same as that line has twofold symmetry elements. So when these three symmetry elements are not mutually independent, any two operation should generate the third symmetry elements by these principles. These are interrelated. Okay, so these are two principles that I want you to remember. Mirror plane with alpha over mu, then this is the same as alpha rotation operation of these two mirror plane intersects, and mirror plane and inversion center is basically the same as twofold symmetry elements. With this in your mind, now I will derive these 32 point groups, and the principles of derivation is like this. Start with pure rotation axis. I explained to you already. There is one-fold, two-fold, three-fold, four-fold, six-fold. And in the multi-rotation axis, there's 2, 2, 2, 3, 2, 2, 4, 2, 2, 6, 2, 2. And there's 2, basically 3, 3, 2, 4, 3, 2 belongs to multi-rotation axis of cubic crystal structures. And these are just composed by the rotation operation. So there are 11 ways of repeating congruent objects about a point. Here, congruent objects meaning that right hand preserves as a right hand. And operation of the first sort is first sort is an operation which repeats an original object to become a congruent object. Right hand, left hand, left hand. Now there are operation of the second sort. That's an operation which repeats an original object to become an enantiomorphous object or incongruent objects. This operation makes right hand to left hand or left hand to right hand. This is what we call incongruent operation or enantiomorphous objects. There's mirror plane and inversion center basically belongs to this one. Now, when I derive these 32-point groups, I would like to relate this with the Schoenflies notation. Schoenflies notation is basically the Schoenflies definition of these 32-point groups. It's treated the crystallographic symmetries as mathematical groups of operations. And in his definition, a group containing only an operation and its powers is called a cyclic group. And the symbol for a cyclic group corresponding to a rotation axis of order n is Cn. So this is a cyclic operation, rotation operation of n-fold. So C1 is just one-fold operation, C2 is two-fold operation, C3 is three-fold operation, C4 is four-fold operation, and C6 is six-fold operation, just a single rotation operation. And now he defines the axial groups containing more than one axis are not cylindrical since they contain more than one operations. And there are two different kinds. This is basically multi-rotation system. A combination of a set of two-fold axes at right angles to a chief axis of order n, which we call dihedral groups of Dn. Okay, so what it means is D2 is principal axis, which is vertical axis, is twofold, and there are two-fold axes perpendicular to this principal axis. Then this is what he calls dihedral groups of twofold. Is basically twofold, and this dihedral group is just follows. So in his definition, D3 is dihedral group of threefold, 3, 2, 2. Dihedral group of fourfold, 4, 2, 2. And dihedral group of sixfold, 6, 2, 2. Remember that when I explained about this multi-rotation axis, there are only certain set of multi-rotation symmetries that is available. One is 2, 2, 2, 3, 2, 2, 4, 2, 2, 6, 2, 2. And there are also cubic symmetries, which is 2, 3, 3, 2 and 4, 3, 2. And he calls it 4, 3, 2 as an octahedral group. And when you learn about crystal structure, there is an octahedral position, and octahedral position has basically these 4, 3, 2 symmetry elements. So that's the reason why he called this cubic symmetry of 4, 3, 2 as octahedral group. And when you learned about crystal structure, there is tetrahedral interstitial sites, and this tetrahedral interstitial sites has this 3, 3, 2 symmetry, or we call 2, 3. I will explain to you about how we change these numbers. So he called this multi-rotation axis, which belongs to cubic, as a tetrahedral group, and tetrahedral site has basically these symmetry operations. Now, with this basis, the Schoenflies notation has another elements in there. With these basic elements, he put the inversion center, then he notated AI. So when there is I, it means that this symmetry, point group symmetry, has inversion centers. And the addition of a vertical mirror plane to the principal rotation axis, he called it V, vertical mirror plane. And the addition of a horizontal mirror plane to the principal axis as a horizontal mirror plane, then he calls it H as a horizontal mirror plane. And the addition of a diagonal mirror plane, and that it means that vertical but diagonal in between two folds, and then he calls it as D. Okay, so Schoenflies notation CN, DN, TO, and he put inversion centers and vertical mirror plane. He put the mirror plane, but how you put the mirror plane has different arrangement: horizontal mirror plane, vertical mirror plane, and diagonal mirror plane. And that's how he systematically defines these 32 point groups. And we'll go this one by one in the next slides. When you do this, basically we can derive these symmetry 32 point groups. Finally, will come in here. Okay, Cn, simple, just cyclic operation of n. As I explained to you, there is a C1 to C6. There's 5 of them. Dihedral groups of n-fold, so there are 4 of them. And cubic, there is tetragonal symmetry and octahedral symmetry groups. So if you combine these, then there are 11 of them. And when we derive these 32 point groups, all the point groups can be derived by putting this mirror plane and inversion center to the rotational symmetries. But there's only one that cannot be derived by that, and that's 4 bar. 4 bar is rotor inversion, and this is the only rotor inversion that cannot be developed by putting inversion center and mirror plane. So this single rotor inversion S4, 4 bar, is defined by him. So there's one of them. Now there's a CNH, cyclic rotation operation of n-fold. Now he put the horizontal mirror plane. CNI, simple cyclic rotation operation of n-fold. And now he put inversion center in there. So he defined it as CNI. CNV is vertical mirror plane. And DNH and cubic in the dihedral group of n-fold, he put the horizontal mirror plane. And in the cubic symmetry also, and then he defined 6 more of point groups. Now D and D, diagonal mirror plane in the n-fold dihedral groups. Then he develops 3 of them, and then we can make these 32 point groups. Okay, so this lecture is basically the graphical illustration of how we derive these 32 point groups one by one. So I will draw a lot of these point group symmetries. And because this point group symmetry is there is a lattice point in the center of this symmetry operation, and we generate poles along these lattice points. So all the objects can be understood by the stereographic projections. Okay? So I want you to follow me one by one. When you do this just shows the symmetry elements of these 32 point groups. Okay, so I will go systematically one by one of these. So let's first go to Cn. Again, there's C1, C2, C3, C4, C6. I don't think, I have to do it again. Basically C4, if you do the stereographic projection, then there is one 4-fold rotation operation. Then when you have one pole, general poles, then this general pole generates 4 folds. So this is C4. C4 is basically the same as 4-fold in the notation wise. C6 is C6. So this one, I'm sure that you already know it, and you already know how to draw it in the stereographic projection. Now let's go to the Dn and the cubic. First the Dn. Okay, so there's Dn, D2, D3, D4, D6. When I explained to you about multi-rotation axis, I explained to you already. This dihedral group of twofold, D2, is basically 2, 2, 2. What it means, then there is vertical principal axis of twofold. Now, perpendicular to this, there are twofold symmetries. So how we define this axis in the stereographic projection? Vertical axis has twofold. Now there is another twofold, okay, in perpendicular to this principal axis. So this axis now is twofold. Then this twofold generates this twofold because this twofold rotate 180 degrees. So one twofold defines this. Let's call it X. When I call this X of symmetry axis, this is just the symmetry axis. Okay? So when I call this axis as X, this one is the same as X because it has twofold symmetry. Okay? But this rotation axis is the same, so X basically, it's the same thing. So one more axis should be defined. That is defined as Y in here, and that's also twofold. In the multi-rotation axis, in the Euler construction, when the system has multi-rotation axis, all these three axes are not mutually independent to each other. And these three axes should be located like that, rotation symmetry axis, and with certain angles. Because that's the only way that just the two operation of the symmetry is the same as the third operation. So you don't have to do the third operation. Okay? So in this case, if I have general Pauli here, twofold makes these symmetries. Now this x-axis operation is using the Wolfnets, and you rotate 180 degrees along the rotation axis, which is in the plane. Then pole is generated here, and this pole is generated here. So multiplication factor is 4. Again, you don't have to do this y operation. You know immediately that there is twofold symmetry in that directions with that twofold symmetries. So multiplication factor is 4, and this is upper pole, and this is down pole, but this is all composed by the simple rotation. So all the right hand is maintained, and this one is right hand, this one is right hand, this one is right hand. All right, D32 is something that need a little bit of explanation. D32 is 322. Okay, in the stereographic projection, how I draw it, vertical axis has threefold. Now, perpendicular to the principal axis, this one says that there's twofold. So there's twofold in here. Now let's call it as x-axis in the symmetry-wise. Then this threefold generates the same thing. So this one is x-axis, and this one is x-axis. So this one is twofold, and this one is twofold. This x-axis symmetry is defined by this second twofold. Then what is the third twofold? Symmetry-wise, third twofold locates at the midpoint of this twofold symmetry. So this one is y, and this one is y, and this one is y, in between these x twofold symmetries. That's how the rotation axis should be located. So this one is twofold, and this one is twofold, and this one is twofold. That's what this 2 says. Okay, now symmetry-wise, if I have general pole here, then threefold generates here, and this threefold generates here. Now this x-axis operation generates down pole in here, and down pole in here. This is all rotation. So even though it's upper pole and down pole, it still has the right-hand side, right-hand operation. Now, as you see, you don't have to do this y operation. You can immediately see that this y operation is already there. Okay, so y operation is already there. So when you do 3 multi-rotation axes, you do only 2 symmetry operation. Then third axis should be there with that symmetry elements. In this case, you see that this x symmetry and y symmetry, which is different in here, is basically the same thing. Rotation axis should penetrate So X, Y is basically the same thing. So you don't have to write down 3, 2, 2. So people write down 3, 2, just blank in here. That explains all the symmetry elements. So this is the international symbol of D3 as 3, 2, instead of writing it 3, 2, 2. Don't have to do it all, but let's do it D6. A little bit complicated. These symmetry elements has 6-fold principal axis. Now if I define one axis perpendicular to this principal axis as 2-fold, which is 6, 2, 2, this one I define it as X, symmetry axis, then this 6-fold generates the X, 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 X in here. So all this X should be 2-fold, 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 2-fold. Okay. Now, what is this 2-fold? This one is what I call y-axis. That's the new 2-fold symmetry that is generated, and that's in between this x-axis. So this one is y, and this one is y, and this one is y, this one is y, and this one is y, and this one is y. That is developed, and that has also 2-fold symmetry elements. That's what 622 designates. Okay, symmetry-wise, you have 6-fold. If I put one general pole, upper right hand, then 6-fold generates 6, and 6 in here, 6 in here, 6 in here, and 6 in here. Now, if I do y-x operation, 2-fold, down pole generates here, down pole generates here, down pole generates here, and down pole generates here, down pole generates here, down pole generates here. So multiplication factor is 12. Again, as you see, that you don't have to do this y rotation operation. You immediately see that y-axis has 2-fold elements in there. Okay, so that's the 6, 6, 2, 2. Now, this is cubic symmetry, multi-rotation symmetry, which is a little bit complicated. Now let's think about this tetrahedral group first. Tetrahedral group, by the Schoenflies notation, is 2, 3, 3. In the stereographic projection, how it looks like, it's basically cubic system. So we have to define the standard cubic projection. Okay, so this is z-axis, and this is x-axis, this is y-axis, and this is, this is one axis. And when it says 2, 3, 3, it has basically 3-fold, 4 3-fold elements in here. Okay, and if one has 2-fold in here, then this 3-fold generates another 2-fold in here and 2-fold in here. Okay, so this one is 2-fold, and this one is 2-fold, and this one is 2-fold, because there's a 3-fold symmetry elements here, and we have one 2-fold symmetry in here. Then this 2 3-fold is developed by this 2-fold operation. But this 2-fold, this 3-fold symmetry should be again defined. So this is what people call 2, 3, 3. Okay. Anyway, if I put the general poles in here, one in here, then 2-fold generates here, this 2-fold generates here, and this 2-fold generates here. Then this 3-fold generates here, here, and this one 3-fold generates here, here. Okay, so this one 3-fold generates here, and then generates here, and this 3-fold generates here, and this one generates here. And then 1, 2, 3, 4, 5, 6, okay, 7, 8, 9, 10, 11, 12. So multiplication factor is 12. And this is T by Schoenflies notation. And when we define this one, people later call it, okay, this is the cubic system. And we wrote it as 2, 3. We delete this. When people write this as an international symbol of the cubic symmetry, the first digit designates 100 type axis. And the second digit generates 111 type axis. Okay, so 2, 3 in the standard symbol, meaning that in the cubic symmetry, the first digit means that all the 100 type of axis has twofold, x-axis, y-axis, z-axis in here, and all the 111 axis has threefold. So this is the notation that people using in international symbols. 432 complicate, again belongs to the cubic. So we start from cubic elements. In this case, this 4 is 100, next one 3 is 111 axis, the next one twofold is 110 axis in the cubic crystal system. All right, so there is fourfold, x-axis, y-axis has fourfold, so this one has fourfold, this one has fourfold. So all the 100 type of axis has fourfold. Now all the 111 type of axis has threefold. Now all the 110 type of axis has twofold. So where is 110 type of axis? This is 110 twofold. This is another 110 type, twofold, twofold, twofold. Now this one is twofold, again 110 type, this one is twofold, this one is twofold, this one is twofold. So that's 432, Schoenflies notation is O. All right, so if I put any poles in here, so fourfold generates 1, 2, 3, 4 by the z-axis, and by the fourfold rotation operation, which is 90-degree rotation operation of x-axis, generates 90-degree upper pole, down pole in here. And again, this one generates upper pole, this is 90-degree, 45 and 90 degrees, so down pole generates here. And this one is fourfold, again, upper pole, down pole generates here. This one is upper pole, down pole generates here. And so far, I did only 100 type fourfold operation of x, y, 001 axis, 100 axis, 010 axis. Now I have to do the threefold operation. When you do the threefold operation, it goes in here. Then this one is upper pole, and this one is down pole. And this one is upper pole, this one is down pole, and this one is upper pole, this one is down pole, and okay, this one is upper pole, and this one is down pole. So it has fourfold symmetry satisfies. Okay, this is the end of symmetry operation. You don't have to do the twofold rotation operation. When you look at it, the twofold operation is already there. All the 110 type of axis has twofold symmetry. So what are the multiplication factors? Multiplication factor is 24. Okay, so when you read this Schoenflies notation and international symbols, you know how to put the symmetry elements in the stereography projection. And when you put any general poles, maximum multiplication generates, then you have to know how to generate these extra poles by this symmetry operation.